start our class for today. So first of all, we're going to be looking at out of the three mode of heat transfer: conduction, convection, and radiation. We'll be looking at the first one today, which is conduction heat transfer. So before we begin, you must understand whatever the definition of conduction is, and you have to thank this person named John Baptist Joseph Fourier. So this is the person who actually discovered conduction heat transfer. So he is a French mathematician and physicist. So back in the day, he was the person who actually discovered conduction heat transfer. Okay? So again, this is the definition again. Conduction is the transfer of heat from molecule to molecule within a substance. And as we said, it is predominantly very prevalent in the solid. We do have conduction in gas and liquid, but it is more dominant in solid. Okay? And then conduction can be steady state and unsteady state. So actually we'll be looking at both of these, steady state and unsteady state conduction. So back in the day, Fourier discovered that the rate of heat transfer by conduction is actually proportional to the area perpendicular to the direction of heat transfer. It is proportional to the temperature difference, and it is inversely proportional to the thickness of heat transfer. So you can see here, this is an illustration on how a wall will look like. So you will have the direction of heat transfer is from left to right, and then the temperature difference is T1 to T2. This is the thickness of heat transfer, and the area perpendicular is the area of the heat transfer. So in order for us to remove the proportionality sign, just now we said that the rate of heat transfer is proportional to something. When we want to remove the proportionality sign, we actually have to add a constant. So in this case, Fourier added a constant of negative K. So Q is the symbol of heat transfer, and the subscript CON here is the identification that this Q is for conduction. So Q CON refers to Q conduction. Is equal to negative K A delta T over delta X. So this equation is known as Fourier's law of heat transfer by conduction. So you can see here we have two examples of how heat transfer can happen using different material. In A, it is for copper, and in B, it's for silicon. Now, this is the main equation for conduction heat transfer, and you have to understand each and every term in the equation. So again, Q here stands for heat transfer. The unit for Q is watt, joule per second, or watt. The unit for K can be watt per meter degree Celsius or watt per meter Kelvin. The unit of A will be unit of area, which is meter squared. ET is the unit of temperature. It can be degree Celsius, Kelvin, Fahrenheit, Fahrenheit, depending on your situation. And delta S is the thickness of your heat transfer, and the unit must be in meter. So we will try to use SI unit. If it's not SI unit, it is highly recommended that you convert everything into SI unit first. So there are two important things that you have to I would like to highlight about this equation. The first one is the value of K. So this K is known as thermal conductivity. So if you remember in our previous class, I did mention to you that in order for you to go through the 7 week with me, there are three major things that you need to understand. The first one is K, the second one is H, and the last one is U. So this is the first thing that you have to really focus on, which is K. So K is known as thermal conductivity. It's a measure of the ability of material to conduct heat. So you can see here, copper has a thermal conductivity of 401, whereas silicon has a thermal conductivity of 148. So you can see here, different material will have different thermal conductivity. Okay, and then the next important thing that you have to understand is that the negative sign. Why we put a negative sign here? So the negative sign in the equation ensures that heat transfer in the positive x direction. So this is the positive x direction from small value of x to large value of x is a positive quantity. So basically, we want our value of q here to be positive. So later on, I'll show you why is negative sign is important. So again, this is just a representation of how the K values vary depending on the material. So the range of thermal conductivity of metal material at room temperature. Okay? A high value for thermal conductivity indicates that the material is a good heat conductor, and a low value indicates that the material is a poor heat conductor, or known also as insulator. So you can see here we have diamond, graphite, silicon carbide, quartz. All these we say are a very, very good heat conductor because the value of K is large. It's around 1000. Okay. Whereas you have gases like hydrogen, helium, and we say they are a very poor heat conductor or very good insulator because it has a very, very low value of K. The second thing you need to know about K is that first thing just now was it is depending on the material. So different material will have different value of K. The second thing that you need to understand is that K is also dependent on temperature. So the graph here shows that how different material interacts with the temperature. So you can see here on your y-axis is the value of K, and on the x-axis is the value of temperature. So some materials are very sensitive to the change in temperature. You can see here, for example, aluminum oxide. At 200 degrees Celsius, the value of K may be around 60 or 70 or 80. But then when you start to increase the temperature up to 1200 Kelvin, the value changes to around 8 or 9. So you can see here, there's a changes from 80 to 8. Whereas there are some material like silver, they are not very sensitive to temperature. So here, to make it clear for you, this is a representation of how K value changes with the temperature. So at 100 degrees Celsius, the K value for copper was 482, whereas for aluminum was 300. And when you increase the temperature, you can see that from 482, it changes to 366. So, two things we have to remember. K value depends on temperature, and also K value depends on the material that you are using. So, in real life, in everyday life, the heat transfer by conduction will happen in all directions. So that's why when we say all directions, we'll have three directions usually. In mathematics, we have three directions: x direction, y direction, and z direction. And this direction is known as Cartesian coordinate. So this is a representation. Let's say you have a box or a wall. So the cube can be coming in from x direction, the cube can be coming in from y direction, and the cube can coming in on z direction. So this, the previous law just now, this is the general equation for heat transfer in the Cartesian coordinates. So dq over dA, q is again our heat transfer, A is our area, K is our thermal conductivity, and dt over dx is how much temperature changes in the x direction. dt over di is how much temperature changes in y direction, and dt over dz is how much temperature changes in the z direction. But since we are just introducing you guys to heat transfer, so we'll only be focusing on one direction, which is our x direction. So we will assume that there is no heat transfer in y and z direction. So first thing that we're looking at in conduction is going to be conduction heat transfer to a plain wall, which is a one-layer wall. So before we start solving questions, before we start using the Fourier's law, we have to make a few assumptions. First assumption, heat transfer only occurs in one direction. Okay, so it's only in X direction. There is no Y direction and there is no Z direction. There is no accumulation of energy in the wall. Okay, so whatever heat is transferred from this direction, all the heat will be removed at this direction, meaning that there is no accumulation. In other words, we are saying that this Fourier's law is for steady state conduction. Remember, conduction will have steady state and unsteady state. So when you say no accumulation of energy in the wall, we are saying that the system is at steady state. And the third thing is that the thermal conductivity does not vary in temperature. So we are even simplifying it even further by saying that the K value does not vary in temperature. So this is an ideal situation. In real life application, K value will vary with temperature. There will be accumulation, which is that most of the time the system is unsteady state and heat transfer will happen in all directions. But for our case, we'll be looking at this. So this is again our first equation just now. Q is equal to negative Ka dt over dx. And then I change the equation. If you look at this into the second equation at the bottom here, Q is still the same, but there is no longer the negative sign. So in the top equation, there's a negative sign. Here is only Ka. And instead of dt over dx, I put delta t over delta x. Now you have to understand what's the difference between dt over dx and delta t over delta dx. So let me just show you how do I get to this equation. Okay, so I'm going to stop sharing so I can show you on the whiteboard how do we actually get from our dt over dx to delta t over delta x. So I'll write again the equation. Q is equal to negative Ka dt over dx. So dt over dx is actually our differentiation. So if you want to remove the differentiation, you have to do integration. So I'm not going to go into detail how do we do integration, but if you're interested, I think you have learned this in mathematics. So by right, you should be able to do this integration. So I'm just going to say that we do integration. So what will happen? So let's say I draw the wall again. Okay. Let's say this is the wall. Okay, so the heat transfer is happening from this side to this side. It's the direction of heat transfer. Our Q, and then we have a thickness of, let's say this is x1, this is x2, and then the temperature here is T1 and the temperature here is T2. Okay, and then the area is this area perpendicular to the heat transfer, which is the value of P. So now, when you do integration, usually this is what you'll get. Q is equal to negative Ka T2 minus T1, okay, over x2 minus x. So you'll get this equation. Now remember, we said that earlier we want our Q value to be positive value. So if you look at this equation, definitely your K value is a positive value. So there's no issue there. If let's say it's copper for 100 something, so it's a positive value. So I can write positive here. A value will definitely be positive. No problem there. Now T2 minus T1. So remember, if you understand the concept of heat transfer and the definition of heat transfer, we say that heat transfer must happen from one system to another system, and heat transfer can only occur from high temperature to the low temperature. So if let's say we are saying that the direction of heat transfer is from point 1 to point 2, we can say that here T1 has a higher value than T2. I can just write here T1 is greater than So let's say we just put a value of T1 here is equal to 100 and the value of T2 here is 50. Okay. So if you look at this equation again, T2 minus T1. So definitely 50 minus 100, you get a negative sign. So you don't want a negative sign. And then again you have x2 minus x1. So usually x2 minus x1 will be a positive value because usually your x2, let's say, is equal to 0.02. Your x1 usually is 0. So 0.02 minus 0 will get a positive value. So this is also a positive value. Now you have positive times positive is positive, positive times negative, negative, negative divided by positive is negative. That is why you have this negative sign. So that negative times positive is negative, times positive is negative, times negative, you're going to get a positive value, and then you divide by the positive value, then you get a positive value of Q. So this is what was meant that you want to ensure that the quantity of Q in the positive x direction is a positive value. So to avoid any confusion, I would suggest you use this equation. Q is equal to Ka delta T over delta x. So when you are using this equation, you just have to make sure that delta T is the temperature difference and delta x is the thickness difference. So it doesn't matter whether you have which temperature is higher, which temperature is lower. Just find that delta T here must always be T, the bigger value of T. So I would say higher value of T minus the small value of T. So if your system, the temperature difference here will be 50. So you don't have to look at which one is T2, which one is T1, which one I have to minus which one. Just take the bigger value minus the small value. So that is why it is much more easier. Instead of using this equation, you use this equation. Again, I'm stressing out, make sure that you understand the significance value of the value of negative. So this, if you're using this equation, it will be easy for you. Just minus temperature difference, meaning that big minus small. Thickness difference minus means that big minus small. Does not matter which one is which one. T1, T2, X1, X2 is just a classification for us. I can also say this is EA, DB. Or I can say DX, DY. Does not matter. Does not carry any meaning. The only thing you have to understand is that big value minus small value, and you must always get a positive value for your Q. Okay, so that is the significance of having your negative sign. So if there's any questions, please, you can unmute your mic and you can ask me. So I can do any kind of, if you have anything you don't understand, so I can just explain it again to you. So let us continue with our class. So this is how you are supposed to get from negative to not negative. Okay, so this is example 1. Example 1 is asking us to calculate the heat transfer through a flat plate of 25 mm thickness copper plate of 200 mm tall and 300 mm wide with a surface temperature of 155 Kelvin and 50 Kelvin. Given the thermal conductivity of copper is 305. So I'm just going to show you briefly how we do this question. So for the next example, you can try it on your own, and maybe in the next class, you can do some discussion on it. So again, Let us just draw our plate. Okay. So we have, the best thing for me is whenever you have a question, try to draw and label everything on the figure. So it will be easy for you to actually see what is the question asking you and what is the question have given you. So for example, now it's asking you to find the value of Q. So we don't know Q. But it has given us, first of all, the thickness, okay, of the copper plate. Thickness is 25 mm. Okay, and then the dimensions, okay, the height and the width of the copper plate. So this is the height, right? This is 300 mm, and then the width. So you can get the area, which is going to be 200 mm. Okay, and then it also gave us the temperature of the surface. It did not say the right hand side or the left hand side. It just said that the temperature of the surface, one is 155 Kelvin and the other one is 50 Kelvin. Okay, so it is up to us whether you want to put the high temperature on the left hand side and the low temperature on the right hand side, or want to put the high temperature on the right hand side and the low temperature on the left hand side. The thing is that if you put like this, then the heat transfer direction is going to be from this direction to this direction. This is the direction of heat. But if you put higher temperature on the left hand side and lower temperature on the right hand side, 155 here and 50 here, so the direction is going to be from left to right. This is the direction of Q. So it is up to you whichever way you want to put it. There's no any fixed rule on saying that heat can only be transferred from left to right. Okay. So now you have everything here. So again, let us write our equation. Q is equal to, so from this point on, I prefer to use this equation. Okay, it is easier for me to use this equation. So I know the value of K is given as 385 watt meter degree Celsius. A is 300 times 200. So it's better if you change everything into SI unit. It will make your life easier. So 300 mm is 0.3 meter. 200 mm is 0.2 meter. 25 mm is 0.05. So now everything is SI unit. Meter, watt, meter, degree Celsius. Okay? And then so 0.3 times 0.2 is going to be 0.06 meters squared. And your delta T is going to be 155 minus 50. Big temperature minus small temperature. So it's going to be 105 Kelvin over the thickness is going to be 0.025 meter. Now, again, I've told you the unit of Q must be watt or joule per second. Okay, watt is equal to joule per second, or sometimes the unit of Q can also be watt per meter squared. So, watt per meter squared, you will use this unit where you don't know the value of A. So, instead, your equation might look like something like this. Instead of Q, it becomes Q over A is equal to K delta T over delta C. When you have this kind of equation, the unit will be watt per square. But in our case, since we know the value of A, so our unit must only be watt So that is our target. You want to get a unit of watt here. So everything else must cancel out. So it's better if you go one by one. So if you have a watt here, okay, this is the unit we want. Then we have a meter. So we have to find a way to cancel out this meter. So if I cancel out this meter, I know I have 2 meter here, meter squared. I cancel out my first meter. And then I go back and I see here you have degrees Celsius. Now, if I look at this whole equation, the only other temperature unit here is Kelvin. So, degrees Celsius must somehow, some way cancel out with Kelvin. So, I don't know if you remember, but you have learned this in your first year, first semester, IT 101. For unit conversion only, you will use this. Okay, 1 degree Celsius is equal to 1 Kelvin. Only when you are using unit conversion, unit cancellation. Okay, if you are trying to change 20 degrees Celsius to Kelvin, then you have to add 273.15. But if you are converting, because this is again our temperature difference. So if you have, please go back and try changing this into temperature, into degrees Celsius, try changing this into degrees Celsius, and then minus this one in degrees Celsius, minus this one in degrees Celsius, you will get the same value here, 105. Because you are just minusing one temperature. So again, for unit conversion, you can use this rule. So if I know this rule, I can just cancel out my degrees Celsius with Kelvin, because I know 1 degree Celsius is equal to 1 Kelvin. And then the other remaining meter is here, and I have 1 remaining meter. So if I go and check again, I don't have any other unit except for my watt unit. So I know that, okay, this is correct, and I can put in my calculator and find the value of, I got the value of 97027 watts. So this is the final value. So this is how to calculate the heat transfer. So please go back and try on your own. And please, another thing I have to emphasize here, make sure you use your calculator correctly. Because there has been cases I have seen with your seniors where everything is right, but they put the wrong value in the calculator and they got the wrong. And then the other thing is that it is very important you have the correct unit. Okay, when we are doing calculation, not only you have to have the correct value, the answer here, but the correct unit is also important. So if you give me the correct value, but the unit is wrong, you will not get a full marks. Okay, unit as important as the correct value. So both must be correct. Then only you get a full marks. Okay, so that is how you calculate your heat transfer, and that is how we solve example number 1. So we have here example number 2. So this one you can do it on your own. Okay, this is example number 1 just now, and then this is example number 2. It is the same thing. Okay, if 3 kilowatt is conducted to a section of insulation material of 0.6 meter squared in cross section area and 2.5 centimeter thick, and the thermal conductivity may be taken as 0.2 watt per meter degree Celsius. Compute the temperature difference across the material. So the question here is asking you to calculate the temperature difference. The value of Q is given, the value of A is given, the value of delta X is given, and the value of K is given. So the question is asking you to calculate the value of delta T. So please go back and try to solve this question on your own. Okay. So now we are moving on to the next part of conduction. Just now we did for one layer wall. Now let's say if you have multi-layer wall. Multi-layer wall meaning that you have a wall made out of different material. So this is a representation of how a multi-layer wall can look like. So for example, you have a wall, and then this wall have a material made up from material A with the thickness, material B with the some thickness, and material C with the thickness. So in this case, we are still saying that it is under steady state. So when we say that it is under steady state, it means that there is no accumulation of heat in the wall. So if we say that, then we can make this equation, meaning that Q total, Q from point 1 to point 4, that is our Q total. Whatever amount of Q is flowing throughout material A, material B, and material C is equal to whatever heat is being transferred through material A is equal to QA, is equal to the heat transferred to material B equal to QB, and it is equal to whatever Q is transferred to material C, which is QC. Okay, so based on that, if you have the equation for QA, QA is equal to KA times A delta TA over delta XA. So the same goes for QB and QC. If you put all the equations, you get this equation. Q is equal to T1 minus T4, A, the highest temperature minus the lowest temperature, over all this for A, B, and C. So this is basically QA, QB, and QC. So by simplifying this equation, you get this new equation. Q over A is equal to delta T overall over R overall. So here we are introducing you a new term for you, which is R. So R is basically, we take analogy from electrical engineering. So if you have taken any electrical engineering courses, R is known as resistance. So we can convert our wall diagram into an electrical circuit like this. So you will have T1, then RA, which is known as the resistance of material A, RB is the resistance of material B, and RC is the resistance of material C. How do you calculate the R? R is equal to delta X over K. So if you want to calculate the value of RA, then it is just going to be delta XA, thickness of A over Ka, which is the thermal conductivity of A. So R total is just RA plus RB plus RC. So that is how you calculate the value of QA is equal to delta T over R. So let's say I will to show you how I get this whole thing again. So this is important. Why? Because you have to understand. You don't have to memorize, but you have to understand how you get that equation. Because sometimes you need to find not only the value of Q, but also you want to find the temperature in between the surfaces. So let's say you have a wall, okay, 3-layer wall. It's now A, B, and C. Okay, so you will have a thickness of right here. This is delta X A, and then it is delta X B, then this is delta X C. We put here this is T1, then this is T2, this is T3, and this is T4. Okay, so sometimes Q is flowing from here to this is the direction of Q. So if you look at the equation just now, it was I said that Q over A is equal to delta T overall over R overall. Okay, so delta T overall will be T1 minus T4. And R overall will be R overall is equal to RA plus RB plus RC. To get the value of RA is equal to delta XA over KA. To get the value of RB is equal to delta XB over KB. And the same thing for RC. So, since we see that it is steady state, there is no accumulation, again, unit is important. So, since it's Q over A, the unit is going to be watt per meter square. Because Q is a unit for heat transfer, A is as the unit of meter square. So, Q over A will have a unit of watt per meter square. T, of course, the temperature for its Kelvin or degree Celsius. Now, R has a whole unit. So, how do we get the unit of R? It's easy, just look at this equation. So, let's say you want to know what is the unit of R. So, you know the unit of your delta XA is going to be thickness as a unit of meter. So, meter, and then you know that the K value will have a unit of watt meter Kelvin. So from here you can know that the unit of R is meter square Kelvin over watt. So this is easy. If you don't remember the units, you can just find the unit based on the equation given. So that is the first thing that I'd like to show you. The second thing is that we know that Q is equal to QA is equal to QB is equal to QC because it is steady state. Now let's say I would like to know the temperature here. Okay, T2. The question usually will give me T1 and T4, but I would like to find the value of T2. So you can use this. Why? Because you know that whatever Q is transferred from point 1 to point 4 is the same Q is transferred from point 1 to point 2. So you can use that. So let's say you know the value of Q over A. Okay, so Q over A is actually equal to QA over A. And then you know, can say that the value of QA over A is equal to delta T A over R A. So you have to understand here, if we are using QA, then automatically will be delta A. Because why? We are only focusing on layer A. Other layers, we are not concerned yet. So if you want to put A here, then it's going to be delta TA over RA. If you want to find temperature here, okay, if you want to find temperature here, so you have two options. Either you want to use T1 or you want to use T4. Okay, so it depends on whatever direction you want to use, but it's still going to be similar to this one. So if you were to write the whole thing, Q over A is equal to delta T A over R A is equal to delta TB over RB is equal to delta TC over RC. And then we can change this one, which we know that delta T overall over R overall. So you can use this kind of equation to find your delta. So your delta TA will be from this point to this point. So this is your delta TA. Delta TB will be from this point to this point, and delta TC will be from this point to this point. So depending, for example, if you want to find temperature between layer B and layer C, yeah, so you need to know the value of delta A and the value of delta B. Then only you can get temperature difference from point 1 to point 3. Or if you're using from this direction, you need to find the value of delta C. Because you know that delta C, you have this temperature value and then you minus the delta C value and then you get temperature at this point. So depending on what direction you are focusing on. So this is important for you to understand. So this is how we actually get this equation. Okay, if you have any questions, anyone understand or you have any questions, you can ask me. Everybody clear? Clear?
Yeah,
Okay, thank you. So I hope you understand this one. And if you look at the slides again, okay, so this is how we're gonna get this one. And then this is an example on how multi-wall plane will question will look like. Okay, so a wall with an area of 25 meters squared is made out of 4 layers. So you have 4 layers here. On the inside is the plaster of 50 mm thick. Then there is brick of 100 mm thick. Then you have insulation of 60 mm thick. And finally you have 100 mm thick brick again. So the inner surface temperature of the wall is 18 degrees Celsius and the outer temperature is -2 degrees Celsius. Calculate the heat loss and the temperature at the interface between plaster and brick. So for this question, I'm just going to show you how to draw and label everything. So I hope you can try to solve this question on your own. And if you have any issues, we can discuss it next week in our class. So you have to really understand and read the question properly and make sure that you get everything. So first of all, it's saying that you have a wall. Okay? The wall is made out of 4 layers. If you have 4 layers, easiest way is that draw 4-layer wall. Label it whatever you want. I prefer to label it A, B, C, and D. So I know that my layer is A, B, C, and D. So the innermost layer, question says that the innermost layer is plaster. So I just put plaster here, followed by brick, followed by insulation, and then followed by brick again. You have to follow the sequence. And then it says that the temperature on the inside wall, meaning that the temperature on the plaster side is going to be 18 degrees Celsius. And then the temperature on the outside, which is the final brick layer, is going to be -2 degrees Celsius. Okay, so this is your highest temperature, this is your lowest temperature. And then the question also said that the thickness of plaster is 15 mm the thickness of brick is 100 mm. The thickness of insulation is 60 mm. And then finally the thickness of brick again is 100 mm. Right? So you have 4 layers and then you know the thickness. So now the question is asking you to find the value of Q. So if you read the question properly, it did not mention anywhere any information about the value of area. So if you're not given the value of area, you can just assume that you're going to be using Q over A is equal to delta T overall over R overall. So when you are using Q over A, unit must be watt per meter square. Okay. So now, in order for you to find Q over A, you need to find your delta T overall and R overall. So delta T overall is easy. You already know the highest temperature minus the lowest temperature. So 18 minus -2, you get 20 degrees Celsius. Okay. Now you have to find the value of R overall. So R overall is equal to RA plus RB plus RC plus R. In order for you to calculate RA, RB and RC, RT, RA is going to be equal to delta X A over dA. RB is going to be equal to delta X B over dB. RC is going to be equal to delta X C over dC. And then finally, RD is equal to delta X B over dD. So once you get the value of RA, RB, RC, and RD, and then you find the value of RO, put it in the equation, and you get the value of Q over A. And in the slide, I've already given to you the answer. Okay, that is for question, first part of the question. The second part of the question is they are asking you to find the interface temperature between the plaster and the brick layer. So that is why it is important for you to report everything. So you know that plaster and brick, this is the interface. Okay. So if you were to label, let's say this is T1, this is T2, T3, T4, and then T5. So T1 is equal to 18, T5 is equal to -2. So you want to find T2. So if we use this equation again, we know that Q over A is equal to QA over A. And this is equal to delta TA over RA. Okay, so this value you have calculated, which is this value, R0 should be able to calculate based on this equation. The thing that you want to find is delta TA first, and RA is already been calculated. So once you get your delta TA, okay, so you have to understand what does delta TA means. Which temperature minus which temperature. So delta TA. So again, delta TA will be around, okay, in this. So temperature from this point to this point. So this is the value of delta TA. And again, delta TA, when we put delta T, you must always have a positive value. So delta T will be equal to T1 minus T. So if you look at the question is asking us to find the value of interface between plaster and brick, which is the value of So based on this one, you can see that T2 is equal to T1 minus delta. So that is how you will get the value of T. Okay. So please go back and try these questions. This is the first example, example 3. And then we have another example, example 4, which is also for multi-layer wall. And then I also added an extra question for you. So example 1, example 2, example 3, example 4 are just example. This is actually a past year questions in which I did for 2018. So this is how you can expect your final exam to look like. So if you are able to do this question, by right, you should have understand everything that we have discussed today. So on Wednesday, our main objective will be to discuss this question and to see whether you are able to do or not. Okay, so is there any questions before we end our class for today? Anybody have any questions?
No question. Thank you.
Okay, just one question. I'll stop the recording first.